I'm going to talk about tidy data and Bayesian analysis, making uncertainty visualization fun. So I actually want to start this talk by asking what happens when we ignore uncertainty. So I'm a scientist, or at least I'm a computer scientist, so that kind of makes me a scientist. There's an old joke, you put science in the name of a field, is it actually a science? So here's an example of an uncertainty display in a scientific paper. A mixed design ANOVA with sex of face as a within subject factor and self-rated attractiveness and oral contraceptive use as between subject factors revealed a main effect of sex of face. F of 1, 1276 equals 1372. P of less than 0.00, no thank you. So a common alternative to this might be something like a regression table. So we theoretically have uncertainty here. There's standard errors in brackets and some asterisks corresponding to p-values or whatever. I mean, this is a visualization conference. We should probably be talking about things like confidence intervals around regression coefficients plotted as a dot whisker plot. This is communicating essentially the same information. If this line overlaps that line, or I suppose if this line doesn't overlap that line, then p will be less than 0.05 over here. And if this line overlaps that line, then p is not less than 0.05 over here. It's getting a little bit more information in there, but you might go a little bit further and stick a likelihood or a Bayesian posterior on top of that estimate. If you don't know what those are, I'll talk about them in a couple minutes, so don't worry about it. Basically, we're getting a little bit more fidelity in there, but still you might ask the question, how easy is it to ignore the uncertainty? And I would argue very. I could just look at this number, that dot, or that dot, and happily conclude, oh, this is definitely not equal to 0, and this is equal to 0. Well, what happens there? You have dichotomania. We love to dichotomize as humans, and what we'll do is we'll say, this is definitely not equal to 0. We'll publish this result, and we won't publish that result, and then we get publication bias. Another example of dichotomania recently experienced by probably the world, predictions from the last US presidential election. So these are poll aggregator forecasts of the probability of Trump winning the election. A lot of people got mad at the poll aggregators because, 28% seems low, therefore I'm surprised that Trump won the election. Well, there was this really nice post on the Washington Post after the election happened, using something called risk communication theaters to try to re-express these predictions. So imagine that I give you a ticket to a random seat in a theater with 1,000 seats in it. And then I show you this and I say, well, I've colored these seats black. If you end up in a black seat, Trump wins the election. If you end up in a white seat, Clinton wins the election. Well, now I don't feel that surprised if I end up in a black seat and Trump wins the election. Maybe over here, the Huffington Post might not be doing too great. So people are very good at ignoring uncertainty, and especially when we provide bad uncertainty representations. The flip side of that is there are actually some good uncertainty representations. So risk communication theaters are just an example of icon arrays. These have been studied extensively in the medical risk communication literature. So we'll use them for things like you're trying to decide which treatment for angina you want to take. And I'll give you a grid of 100-odd people and color them in depending on whether or not they were successfully cured, or perhaps other things like complications or such that may happen. This makes it a lot easier to imagine how likely is it that I'm going to be one of these people rather than some probability of an outcome, which is more abstract. This is called a frequency framing or a discrete outcome visualization of uncertainty. So you can actually do this for continuous distributions as well, although it's a little bit more complicated. So here's an example of some stuff that I've worked on in communicating probabilistic predictions of bus arrival times. So typically, systems that do real-time tracking of buses will communicate predictions in this way, which is somewhere between now and the future. I'm going to predict your bus is showing up in exactly 11 minutes. This is a rather poor low fidelity representation of a prediction. Something better might be a probabilistic prediction, so there's some chance your bus will show up in this time period. It's most likely at this time. There's a bit of a long tail, and maybe even 20 minutes from now, your bus might be running late, hit traffic, whatever. But we want a more discrete framing of uncertainty so that people can understand it better. One of the things we could do is take the cumulative distribution function, so basically the probability that the bus shows up before any given point on this timeline, take evenly spaced quantiles, stick them back into the time domain, and then stack them up into a dot plot. This is called a quantile dot plot. The nice thing that happens, there's a couple of useful properties of this visualization. One of them is that the shape still approximates the density, so you can still find things like the mode if you want to. But if you want to do interval estimation, which really matters here because what I actually want to know is, say, if I show up 8 minutes from now, what's the probability I catch the bus? Well, there's 20 dots, and I just count up how many dots are on one side of that line. I will miss 2 of those dots, or I will get 18 out of 20 of those hypothetical dots, which means I have a 90% chance of getting the bus if I show up 8 minutes from now. It turns out if you use representations like this, people make better estimates. They can extract probabilities better from these visualizations. They can also make better decisions. So we've run incentivized experiments on these sorts of things. They make better decisions, and also even the worst performers improve. So people can learn how to use these sorts of things. So all of this is to say good uncertainty displays are possible. They're also typically a little bit weird. OK, so sure, we should visualize uncertainty. But it's kind of a pain to build these things. So what I wanted to do with this talk was say, what are some strategies for actually building them and prototyping them rapidly so that you don't have to spend all your time trying to figure out how to put the visualization together so that you can actually play with things you want to play with. And the 3 components of the strategy that I've kind of developed over time doing this are these. So the first is to use Bayesian analysis in order to get samples from probability distributions to feed into the rest of the pipeline. The second is a particular strategy for using tidy data to organize those samples. So tidy data being this idea of usually 1 observation per row in a data frame. And then using grammar of graphics-based approaches to visualize those samples, or to specify visualizations for those samples. And I tend to use ggplot, but you could certainly do something like this with Vega Lite or Altair. I think the nice thing about the grammar of graphics is it's kind of spreading everywhere, and so it's a very useful way of thinking about visualization if you want to prototype across many tool sets. OK, so step 1, Bayesian analysis. This is going to be the possibly rough part of the talk. So I'm going to go through an example of kind of how Bayesian analysis works, and if you're already familiar with it, I'll gloss over some things and you might get mad at me, and if you're not familiar with it, I hope I don't lose you. The end point of all of this is supposed to be that we are able to generate samples from probability distributions that describe our uncertainty in things. That's the high-level part of this that I'm going to try to get through. So let's say I was running an experiment, and I have 2 different, say, interfaces, B and A, or A and B, as you like. And I want to estimate the mean difference in people's time to complete some task in seconds on these 2 interfaces. And so I've gotten a bunch of people to use both interfaces. I've been sensible and like counterbalanced it and all that stuff. And each of these dots represents, say, this person took 6 seconds more to complete the task on B than they did on A. Oh, sorry, I mislabeled these. B is faster on that side, A is faster on that side. I changed this label at some point. Right, so what I want to know is the probability of the actual mean difference between these 2 things given the data that I've observed. And of course, any card-carrying frequentist statistician will tell you you can't do that. So what we're going to do instead is figure out what the probability is of seeing this data given various different possible mean differences between these two. So I'm going to wander along this space and ask, for every possible mean difference between these two treatments, what's the chance of me seeing a sample that looks like this? So obviously over here, it's pretty low because I'm pretty far from what the sample mean is. And it would be kind of unusual for the true mean to be here and for me to get a sample that looks like this. So this is pretty low. I continue wandering along. As I get closer to the sample mean, were I to hypothesize that this was the true mean, it's reasonably more likely that I can generate data that looks like this. At the sample mean, it is most likely, and then it falls off symmetrically on the other side. So this is called the likelihood. This is the probability of seeing this data given some hypothesized mean difference between these conditions. But as Heather helpfully informed us yesterday, were I to take this quantity as representing this quantity, I would be committing the prosecutor's fallacy. And that is exactly what you do when you look at a frequentist estimate and confidence interval. If you really want this quantity up here. The problem is, in order to get that quantity, I need something else. I need to have some prior knowledge about this domain. Here's a hypothetical prior. Perhaps this is a well-studied domain, and we know that the time to complete this task is, on the order of 4 to 6 seconds on average in most conditions, and differences between that are basically never greater than 4 or 6. So I could come up with some reasonable prior that's just, I'm agnostic to which one's better, but I would be really surprised to learn that one of them is better than the other by like 8 seconds, right? So here's a maybe reasonable prior for this data. And then all I need to do is multiply these two curves together. So I could wander along and multiply these together, and I get something like that. And this is my posterior. So given what I thought before running this experiment and the evidence that I saw in the data, what do I think the mean difference is? You'll notice in this case, because I think that these are quite unlikely, my estimate has been moved a little bit towards 0. If you're in the machine learning mode, this is essentially like regularization. I am less happy to glom onto variance in this data as I observe things, and so I can reduce variance by adding just a little bit of bias to my estimates. So the other thing that I wanted to show, though, was, of course, this depends on what my prior is. And one of the other ways of looking at this is my frequentist estimate is what I get if I believe that every possible value on this line from 0 to infinity or all the way back down to negative infinity are equally likely before I look at the data. And in most cases, I contend that that is a obviously false assumption. I do not think that it's very likely that the difference between these conditions is on the order of even more than 12 seconds, but definitely not 12 million seconds. And as I make my prior a little tighter, my posterior will shrink towards 0. And so I'm essentially trying to balance what I know before looking at the data with what I learn from looking at the data. Okay, so that's a basic idea of Bayesian analysis. But again, as I said, I don't really want to spend a lot of time on the technical details, but to say that the thing that you really want to know about are given all of this machinery, we can then generate a whole bunch of samples from this posterior distribution that can represent our uncertainty and say what we think the mean is. And the nice thing about using samples is, one, there are a lot of posterior distributions that we can't calculate analytically, but can, through clever algorithms, draw samples from. So that's useful. The other thing is, there's a lot of nice things that I can do with posterior samples that make reasoning about probability here a lot easier. So I can just count, if I have like 10,000 samples here, I can just count the proportion of them that are greater than 0, and that will correspond to the probability that that mean is greater than 0. Or even greater than 2, if 2 is, say, an effect size that I actually think is meaningful here. Okay. So we have our posterior samples that represent our uncertainty. Now the problem is we want to visualize them in useful ways. We want to make some of those interesting visualizations of uncertainty, and we don't want to spend all of our time munging data to do it. So let's actually start and just try to build this chart in the bottom left-hand corner. So how are we going to do that? Well, one way of doing this is I will pick some grid spacing and just grid over the x-axis, and then build a table. So I'll have this table that goes from 1 to 10 with some spacing, with a bunch of rows omitted because I don't have the space on this slide for that. And then let's say I want to know this red line. Maybe I'll just go and poke my model and say, what do you estimate the mean to be at each x position? The problem is this is not going to generalize as a way of allowing me to generate other interesting uncertainty visualizations. So this is not a good approach. At least that column, the second column, is not a good approach. What I can do instead is the same idea. I grid over this, but then for each one of these, I stick in however many rows that there are samples in my model, and stick in a whole bunch of samples representing the uncertainty here, and then here, and then here, and then here, and so on. So now I end up with this table that's got, you know, a couple 100,000 rows or whatever. And then what I can do is, I should also mention the TidyBase package in R, which I've been developing, outputs stuff like this, so you don't have to do it manually, which is really the annoying part in existing Bayesian samplers in R anyway. So then the question I can ask is, what aggregation do I do, and how do I map the resulting data onto useful channels and marks in order to get this visualization? And the nice thing is that pretty much every useful uncertainty visualization can be fit into this sort of framework to get that table to generate a useful chart on this side. And that brings us to the grammar of graphics. And in this case, I'm not going to go formal with the grammar of graphics. I'm just going to say something like, within each of these groups, I'm going to take the mean and 95% interval, and then I'm going to map those onto a line geom or mark, depending on which toolkit you're using, and a band. And that gives me this chart. But then the part that makes this useful is, what if instead I wanted to do a frequency framing version of this? I wanted to give you examples of a bunch of different possible regression lines. Well, all right, okay. So instead, in each of these buckets, I'll just take the first 100 samples, map those onto a line geom, and group each one by sample. Now I get 100 approximately equally likely regression lines as a visualization of uncertainty here. The nice thing about this visualization is it's really hard in comparison to this, where I can ignore this band, for me to just say, well, I'm just going to take this line in the middle. I can take that a step further. Oh, actually, I'll get back to that. So this is a really interesting approach called a spaghetti plot. It's been used in hurricane prediction visualization. So one of the problems with visualizations like this is people make what's called a deterministic construal error. So they think that this is predicting that the hurricane is getting larger over time, and it's not. In fact, once it makes landfall, it's going to get smaller. So it's giving you the opposite inference. But you might replace that with something like this, where I'm giving you a whole bunch of possible paths instead of the error count. Right, but I could go even further and say, I'm going to do the same mapping, same geom, but instead of collapsing all of these into one chart, I'm going to map each sample onto a different frame. Now I get an animated visualization of uncertainty, where it's even harder for me to ignore the uncertainty. I should say that all of these changes amount to about 1 to 2 lines of code difference in these charts. With the addition of the ggAnimate package, it essentially adds a fake aesthetic or visual channel which corresponds to time. And so now I just map what I want onto time and I get a bunch of frames. So now it's really, really hard for me to just take one line and ignore the uncertainty. And the nice thing is that that data structure doesn't change for all of these charts. There's just a bit of aggregation in the pipeline and then some grammar of graphics on top of it. But on the subject of hops, so we had a nice discussion yesterday about the New York Times election needle. I actually like the reaction to the New York Times election needle. I think this one's my favorite. The New York Times needle jitter is irresponsible design at best and unethical design at worst, and you should stop looking at it. I actually disagree with this. I think that I think that one of the things that the New York Times election needle did is it made a whole bunch of people anxious, and it made them anxious because they couldn't ignore the uncertainty. So really, we want anxiety to be proportional to uncertainty in the case where it's something we actually care about, which I think a lot of people cared about that election. I'm just guessing. Okay. So I think that tidy tables of samples are a powerful and generic way of building interesting uncertainty visualizations. Here's a bunch of other examples that are all just minor tweaks on same sorts of pipelines. So you can do quantile dot plots by just aggregating those groups into quantiles and then making a dot plot. You can do so over there we have predictive distributions, so that's giving predictive bands into which we think new observations should fall with some probability. In the bottom we have multiple groups having different regression fits. You'll also notice that now it's a curve instead of a line, and because we were doing that gridding, it just works. And the addition of another group just means another column in your data frame of predictions, and then you facet over it, so it's like maybe 2 extra lines to generate that chart over the one where you don't have a group. So yeah, so all of these visualizations are generatable through the same basic pipeline. It's posterior distributions as samples into tidy data frames into grammar of graphics. So to conclude, I think that uncertainty visualization can be fun. And that Bayesian analysis, tidy data, and the grammar of graphics make it an easier to explore design space. And maybe with that, we'll start to see more New York Times election needles. Or not, as you wish. Thank you.